Now I want to turn to introducing the theory of statistical mechanics. So for this we're going to look at the PowerPoint presentation I made. So the idea is that you can describe the statistics of a system with a large number of particles, in this case it's a kind of model of a gas. So you can describe the thermodynamics of such a system in terms of the statistics of what its particles are doing. That's the basic idea. So in this particular example, we consider particles in a box where they move with a constant velocity unless they collide. And if they collide just like pool balls, elastic collision. So if you look here, you can see lots of different collisions between the particles. And you assume those are elastic. So this is a model of a gas, a classical model of a gas. And I want to look at its statistical properties. So first of all, we can describe the microstate. Classically, so the microstate is a complete determination of the state of every particle in the system. So I tell you exactly what that system is doing. Classically, in that case, I should tell you all of the velocities and all of the positions. Quantum mechanically, though, because of the uncertainty relation, I only have to tell you one set. So if this is a quantum mechanical problem, for example, I could just tell you the velocities of each particle in the gas. And that would give you a complete description of the state of this gas. I tell you the velocity of every particle in it. If we assume this system is closed, that means no energy or momentum is transferred in or out, then the total kinetic energy must be a constant. And kinetic energy is a half mv squared. So you can ignore m if it's a constant, so I get that this must be a constant. But if you look at the picture, the animation I showed you on the previous slide, you see that the microstate is changing. I defined the microstate in terms of the velocities of the particles, but when two particles collide, they change velocity. Right? So this particle is now moving up, but when it collides with another particle, it suddenly starts moving horizontally. So collisions change the microstate of the system. So each collision changes the microstate of the system. For example, I have two particles here with velocities v1 and v2. Initially, after they collide, they have some other velocities, v1 prime, v2 prime. So the microstate has changed. Now I draw this symbolically like this. Okay? The system starts off in some microstate with these velocities, and it ends up in some other microstate with some new velocities, with the primes here. So the state of the system is changed by collision. So as I go through the whole thing, each time there's a collision, the state of the microstate of the system is changed. Each time two particles collide, the velocities of the system is changed, and therefore the microstate the system is in is changed. So I can describe the evolution of the system in terms of the microstate it's in at each particular point in time. And each time there's a collision, the microstate is changed. Now, if I'd started the system with the particles in a slightly different configurations of positions, then other collisions are possible. Right? If I'd scattered them in a different way and run the same simulation, then I could have got different results. So, for example, instead of going from this microstate into that microstate with a collision like this, I could have gone into a different microstate with a different kind of collision. So there are lots of different possibilities, different possible ways of going between microstates. So you get this big complicated network, and each step is reversible. So if I can collide in this way, like that, I can also collide in the opposite way and go back into the same state. So as I go forward in time and the collisions happen, I get this complicated network of microstates where I can scatter through collisions between the microstates in the network. Is that clear what's represented there? Each dot here is a statement about the velocities of every particle in the gas. When there's a collision, the velocities change, and I go into a new microstate. So each time there's a collision, I go into a new microstate. Okay. I want to give a completely different example as well to give you the idea of how this abstraction helps. So another example I can consider is a paramagnet. A paramagnet is a material, something like iron, where each atom has a spin, so each atom has a magnetic moment, but at room temperature, there is no net spin. So at room temperature, the directions of the arrows are random. Some of them point up, some of them point down. Yeah, the direction is random, and we can assume that there's, well, for the ideal paramagnet, there's no interaction between the spins. So in this case, a microstate of this system is, I tell you what every arrow in the system is doing. So I say the first arrow is up, second arrow is up, third arrow is down, fourth arrow is up. That's a microstate. I tell you exactly what the system is doing. And how does the system evolve? Just like the gas can have collisions, I imagine that in this system there can be spin flip events. So at some point in time, one of the spins can suddenly change direction. So if it was pointing up, the spin direction can suddenly change to down. So in this case, I started out in microstate 1 where this arrow is down, and I went to microstate 2 where this arrow went up. So you see in this way again, you get a network of different microstates and different ways of going between them. For the case where I only have 3 atoms, it's so simple I can actually draw the picture. In this case, there are 8 different possibilities. Right? Each spin either points up or down, so there's 1, 2, 3, 4, 5, 6, 7, 8. And I can draw them on the vertices of a cube, like this. And each time a spin flip event happens, I can go from this microstate, say, into this microstate, then to this one, then to this one, this one. So each time a spin flip happens, I change microstate by moving around the edges of this cube. Okay. So our general assumption is that any system can be described like this. For any system, there's a large number of microstates of that system, which I draw symbolically as these little dots. These little blue squares are microstates. So for a gas, this is telling you the velocities of all the particles in the gas. For a paramagnet, it's telling you the direction of all the arrows in the paramagnet. But it's a complete specification of the system. And we assume that there's a large number of them and that they're connected in there's a large number of connections between different microstates. Then, as time goes forward, the system changes microstates. So each time there's a collision in the gas, you change microstates. You move around this network. And we assume that this happens very fast. So in a gas, the number of collisions is very, very large. There are millions and millions of collisions every second in a gas. So you go through these microstates very, very quickly indeed. The scattering is very fast. Finally, we assume that the changes between microstates are reversible. That means if I started in this microstate and went into this one, it's possible sometime later that I can go back to the original microstate with the same probability. If I go one way, then I can go back with the same probability. Okay, so this is our general abstract picture. So there are 2 terms which are very important. The first one is the microstate. The second one is the state. Okay. Microstate is a complete specification of every particle in the system. So I tell you everything there is to know about the system. I completely specify state. I completely specify every particle in the system. And for example, in a gas then, this means I tell you every velocity. So I tell you what's the velocity of the first atom, what's the velocity of the second atom, and what's the velocity of the nth atom. I completely specify the system. Whereas the state, in this technical sense, is those properties of the system which you can see on a large scale. So large, and the technical word that's used for this is macroscopic properties of the system. Okay. So again, for a gas, state properties we're talking about are things like what's the temperature of the gas, what's the pressure of the gas, and so on. What's the entropy of the gas. The whole point of statistical mechanics, statistical physics, is to give you a way of going from the statistics of the microstate into the behavior of the state. So if you tell me, at a certain point in time the velocities are all like this, how can I calculate from that information the temperature and the pressure of the system? That's the goal. If I know the behavior on the microscopic scale, how can I derive the behavior on the large scale? Now, critical to this is the point on the last slide here. If I have a network which looks like this, and we assume that this is a reasonable model of any kind of system, where there's a large number of points and I scatter between them, if these three things are true, the number of microstates is large, the system changes very quickly each time there's a collision, and the probability of going both ways is the same, then suppose at time 0 I ask you what state the system is in, microstate, and you say it's here, for example. Then 1 second later, I ask you where's the system now. So I start off in this state, this microstate. 1 second later, I ask you where's the system now. Because there have been many, many changes in microstates within that 1 second, and because these changes have equal probability in both directions, you can show that it has equal probability of being anywhere. So I start out here, then I start to scatter, and I scatter all around this network, and then I suddenly shout, stop, and we see where we arrive. Then, if these conditions are true, then I have equal probability of being anywhere within this network. Now, this result is known as the fundamental postulate of statistical mechanics, and it says the following. If I have such a network of microstates, and I let it run for some time, and then I stop it and look at what microstate it's in, then they all have equal probability. The probability of being any particular microstate is equal. So in this case, suppose I have 20 microstates here, the probability of each microstate is 1 divided by 20. They all have an equal probability because of the nature of the scattering between different microstates. Now this, as you can probably guess from the name, it's called the fundamental postulate. This is the most important idea in order to be able to derive the large-scale properties of a system from its microstate. So what we're going to do for the rest of this class then is look at some simple examples of systems where we characterize the full microstate and then use this fundamental postulate to show that what the large-scale properties may look like. So this is the goal of the rest of the course from now on. Okay, before we take a break, I just want to do one very simple example of how this fundamental postulate comes about. A very simple example, but one which will capture all of the important points of the fundamental postulate. So I'm going to take a very, very simple system where there are only 3 microstates. So if I continue using the coloring that I used in the See, there are 3 microstates. Let me draw it a bit bigger. There are 3 microstates like this. Number 1, number 2, number 3. And I suppose I can scatter between them, so if I'm in this state, I can go this way or that way. I can go this way or that way. That way. And I could also scatter back into the same microstate. This. So this is a very simple version of that network I showed you on the PPT. Right? There are 3 microstates, and there are various ways of scattering between them. So I can describe you the probability of changing between microstates by using transition probabilities. So the transition probability between microstates is constant in each time step. So we assume that in one time step, there's one transition event. Each time I click my fingers, the microstate will either change or decide to stay the same. And I give as an example some probabilities. Suppose I start in microstate 1, then a transition event happens. I suppose that the probability I stay in microstate 1 is 3/6, or a half. Right? I suppose the probability I go from microstate 1 to microstate 2 is 2/6, and I suppose the probability I go from state 1 to state 3 is 1/6. So I started in microstate 1, I have a half probability of staying there, a third probability of going to microstate 2, and a 6th probability of going to microstate 3. Now suppose I start in microstate 2. Then the probability I go back to microstate 1 must be the same because of this reversibility condition. So the probability I go from 2 to 1 is also 2/6. But the rest is I can choose freely, so I assume the probability I stay at 2 is a 6, and the probability I go to 3 is 3/6. And therefore, if I start at 3, just to make sure the total probability is 1, the probability I stay there is 2. So this completely defines a network of microstates, 3 microstates, with per unit time the probabilities of transition between them. So I just want to see what happens as I take time steps forward, as the system evolves. Okay, so we may as well start in number 1. So we're going to start in microstate 1. Now what does it look like after one time step? Well, after one time step, I have a scattering event. I could either stay there, or I could go into states 2 or 3. The probability I stay there is 3/6. The probability I go to number 2 is 2/6. The probability I go to number 3 is 1. So, let me write it this way. The probability to be in microstate 1, I'm going to write it this way. The probability that after one time step, I'm in state 1, is just 3/6. Similarly, the probability to be in 2, so this is the probability that after one time step, I'm in state 2, this is 2/6. And the probability to be in microstate 3 is 1/6. Hopefully that's clear, right? After one time step, I started here. After one time step, the probability I stay there is 3/6. That's this. The probability I went until number 2 is this. probability I went into number 3 is this. So that's very simple. It gets more interesting as we keep running. Okay, so this is 0.5, 0.33, this is 0.17. So now we do the calculation again. Again, we have a scattering event, so after 2 time steps, what does this look like? Well, I'm going to write this now, probability after 2 time steps, I'm in state 1. Probability that after 2 time steps, I'm in state 1 is 1. Now this is a little bit more complicated because after 2 time steps, there are different ways of going into state 1. I could have started in state 1, then stay in state 1, then stay in state 1 again. So I could go 1, 1, 1. This probability is just 3/6, that's the probability that I stay there, times the probability that I'm already there, which is that. So this is the probability that I was in 1, then I stayed in 1, then I stayed in 1 again. But also, I could have started in 1, then gone to 2, and then gone back to 1. So I could have gone 1 to 2 to 1. This is therefore the probability of going from 2 to 1 is 2/6. The probability that I was into is P1, 2. So this is the probability of going from 1 to 2 to 1. And then finally I could go from 1 to 3 to 1. And this one is 1/6, 1, 3. And if you work this out, this turns out to be 14/36, which as a decimal is 0.39. So I'll just do one more, and then hopefully the pattern will become clear. After one more time step, I can just reuse this formula, right? This is now an iterative formula. After 3 time steps, I just change this to 3, change these to 2. Finally, after 3 time steps, the probability that I'm in 1 after 3 time steps is this. The probability that I was in 1 and then I stay in 1 plus the probability that I was in 2 and went back to 1 plus the probability that I was in 3 and went back to 1. And again, if you use these numbers, this one turns out to be 75/260. So the decimal is 0.35. Okay? And we can do it for the other ones. The probability that after 3 time steps I'm in 2. Okay. I won't bother to write the formula again. Turns out to be 72/216, which is a decimal is 0.33. The probability that after 3 time steps I'm in state 3 is 69/216. Okay, so the point I wanted to make here is to look at the numbers of these probabilities. After 1 time step, they're all quite different. Okay? This one is 3 times more probable than this. So after 1 time step, these numbers are all quite different. But after 2 time steps, they get more similar. Okay? And after 3 time steps, they get more similar again. So hopefully you can believe me, and it's not too difficult to prove mathematically, that if I do 4, 5, 6, 7 time steps, then these numbers will all converge to the same number. So all of these numbers are converging to t is equal to a third. As the number of time steps increases. Okay. And this is the point of the fundamental postulate. If the number of time steps is large, if the number of collisions or whatever which happen within my measuring interval is large, then when I sample the system, I find the microstate of the system, it has equal probability of being in any microstate. So that means they all have equal probability. Okay. And this is exactly the statement of the fundamental postulate. The probability of each microstate should be equal. And we saw that in our model system, this is true. And what are the important properties of the model system? Firstly, that you have a large number of time steps to get equal probability. And secondly, the probability of going from 1 to 2 is the same as the probability of going from 2 to 1. It has this reversibility. And as long as these things are true, then you will get equal probability of each microstate. This is the content of the fundamental postulate. So I now want to show you a PowerPoint presentation where I do the same kind of thing, but on a very large scale system. So here in this slide, you can see there were 100 microstates, and I've arranged them in a circle just for clarity. So these are 100 microstates, and I get the computer to, at random, make 300 connections between them. So I get the computer at random to choose 2 microstates and draw a line between them. Okay, so, for example, the first microstate starts here for some reason. I connect it to 1, 2, 3, 4, 5, 6 other microstates. Like this. This is chosen at random. Then the next one I connect like this. That means that this microstate, it's possible to scatter from this microstate into this one and back again. So just as I drew a line here from state 1 to state 3, that means the same thing, right? I can go from state 1 to state 3 and back again. On the computer simulation, I can go from this point to that point and back again. So I go around the circle and fit it all in, and when you finish, you end up with quite a mess. So this is 100 microstates with 300 connections between, 300 possible ways of scattering. And I do exactly what I calculated before in the class. I started a particular microstate, and I say that in each time step, the probability to change microstate is 1 divided by a certain number. I think in this simulation this is 11, 1 divided by 11. So there's a certain probability to change, and I see what happens. So I start in microstate 10 for some reason. No way, I start in microstate 10. After 1 time step, I maybe scatter. So I'm still probably in the same microstate with probability about 0.45, but I may have scattered into one of these other microstates, which have probabilities about 0.9. So this is after 1 scatter event. After the next event, it looks like this. Okay? So here it gets more complicated. There are other microstates. Some have quite a large probability, some have small probabilities, but there are a large number of microstates I could be in. As I keep doing the time steps now, after 5 it looks like this. You can see there's still quite a big variation between them. After 10 it looks like this. Now they're starting to get more even. And if I keep running, 20, 30, I go. And after 100, you see that they're virtually all the same probability. So in this simulation, after 100 time steps, I end up with virtually all the same probability. And this again is the fundamental postulate. After I scatter a large number of times, I have equal probability to be in any microstate. Now, this is kind of related, it's not so essential, but it's interesting. There are some issues in this if the number of possible ways of scattering is not large enough. So in this case, again I took 100 microstates, but I only made 80 connections. So you see there are far fewer lines in this case. Now in this case, the behavior is a little bit different. After 10 states, it looks like this. After 50, like this. After 100, like this. So remember in the previous simulation, where there were 300 connections, after 100 time steps, it was virtually all the same. But if the number of connections is small, then after 100 time steps, there's still a big difference in probability. And after 200 still, it takes until about 500 time steps until I get roughly equal probability. So, if the number of connections or the type of connections is limited, then the convergence is slow. It takes a long time to get this equal probability of microstates. And secondly, not all microstates can be reached. You see, there are some microstates here which have 0 probability. The reason for that is easy to understand. If you look at the original network, you see that some microstates are impossible to reach, right? Like this one here, I can't get into it. There's no line connecting it, so I can't possibly get there. These are the same. This one's the same. There are also other microstates which only have one possible way of scattering. So, if you look at this one down here, this one can scatter into this one, but that's it. So these two microstates can only scatter between each other. They can't go anywhere else. So if the number of connections is not large, you can get kind of stuck. You can't reach all the possible microstates. Well, I mentioned this because this kind of behavior is important in phase transitions. What happens in a phase transition, for example, when gas turns into a liquid, is that some parts of the space of microstates become inaccessible. So there is some separation between microstates you can reach and those which you can't. Something similar to this behavior.